Hello dear friends, welcome to this lecture of the Riemann integral. We are proving the existence theorem of Riemann integral. In our last lecture, that is lecture number 7, we have proved one part of the theorem, and now the theorem is here. The statement is f is a bounded function on the closed bounded interval a comma b, then f is Riemann integrable if and only if f is continuous at almost every point in the closed interval a to b. Now earlier we have proved the first part in our 7th lecture, that is f is Riemann integrable, then f is continuous at almost every point in the closed interval a b. Now today in this lecture we shall prove the converse part. That means we shall assume f is continuous at almost every point in the closed interval a b, and then we shall prove f is Riemann integrable. But to prove the converse part of the theorem we need a lemma. I have written the statement of the lemma here. First we shall prove the lemma and then we shall prove the converse part of the theorem. See what is the lemma. If oscillation of f at x is less than a for each x in a closed bounded interval j, then there is a subdivision tau of j such that upper sum minus lower sum on the subdivision tau is less than a into length of j. So we shall prove the lemma, that is the proof of the lemma first. Now for each x there exists an component interval ix. We can consider, see, suppose this is the interval j, and that interval is divided in parts. See, these are the components of this interval j. So for each x belongs to the component interval ix, where ix is a component interval of j. That means suppose ix is somewhere here, this is ix we denote, and there is x point in this ix. We have, by the condition given, the oscillation at each point for each x in the closed, if x lies in this j, then oscillation of f at x is less than a. So therefore we have oscillation of f on the interval ix is less than a. In this interval, x is in ix. Now j is see, closed bounded interval, therefore j is compact. Since j is closed bounded interval, j is compact, and therefore this j can be covered by a finite number of component intervals ix. Therefore there exist a finite component intervals finite number of component intervals, and we denote this by i1, i2 up to in. There exists finite number of component intervals i1 up to in, and of j, and let tau be subdivision, let tau be the points, the subdivision having points of the end points of these intervals. Endpoints of these subintervals, and now we have oscillation of f on each interval, that is ik, is less than a see, oscillation of f on ix is less than a for each x belongs to ix, and therefore oscillation of f on each ik is less than a for k taking value 1 to n. Now what we shall consider is the upper sum of f on tau minus lower sum of f on tau. Therefore upper sum of f on tau minus lower sum of f on tau, and that is, so this is we know by definition it is summation of k taking value 1 to n oscillation of f on ik into length ik. Now see, each oscillation is less than a for k taking value 1 to n. So therefore this in this sum, that is oscillation of f1 I1, oscillation of f1 I2, etc., each is less than a, and therefore we can write this number, replace this oscillation by a, which will be less than a, and what remains inside sum is, this is less than a, and inside sum that will be length ik, k taking value 1 to n. And see what is the length of all these component intervals, that is, so this will be I1 and this is In. So that will cover the whole j, that is sum of lengths of these intervals is j, and this is equal to a into length j, or that is, this is, or we can write upper sum of f on tau minus lower sum of f on tau is less than a into length j, because sum of these intervals, sum of lengths of these component intervals is equal to the length of the interval. So this proves the lemma. So because we are using this lemma in the converse part, we have proved this lemma. Now we shall consider the proof of the converse part of the theorem. Now proof of converse. So I shall write now the proof. We have to remember this statement of the lemma. Proof of the converse part. Converse part, that means we have to assume the second part of the statement of the theorem. That means suppose now f is continuous. F is continuous at almost every point. In the closed interval a comma b. We have to prove that f is Riemann integrable, or f belongs to this class of Riemann integrable functions. F is Riemann integrable on the closed bounded interval ab. And now when we shall say f is Riemann integrable on the closed bounded interval ab, we use here the condition that we have proved in theorem 1. So that means a function is Riemann integrable if given epsilon greater than 0, that is, this is by theorem 1. So by theorem 1 we shall show that given epsilon greater than 0, there exists, or there is a subdivision sigma of the closed interval a comma b such that, so this is to be proved, that we should first mention, such that upper sum of f on sigma minus lower sum of f on sigma is less than epsilon. So if you prove this, then we say that f is Riemann integrable. F is Riemann integrable on the closed bounded interval ab. Now we shall fix epsilon. So given epsilon greater than 0, suppose given epsilon greater than 0, there exists, there is, we shall take m, there is m belongs to I such that the length of the interval is b minus a. the interval is a to b, the length of this interval will be b minus a, and that length divided by m will be less than epsilon by 2, in such a way that we should select m. Epsilon is given, we have to now select m that it is a sufficient number such that b minus a, if you divide by m, then it becomes less than epsilon by 2. That can be selected as depending on epsilon. So, we shall suppose this relation we shall assume as 2. Then if this sum is considered as epsilon, this b minus a, this term b minus a divided by m is less than epsilon by 2. Now, we define em as in the first part of the theorem. Let em be the set of as in the first part of the proof. First part of the proof. So, but what is that em? That is, em is the set of points of the interval a b at which the function is not continuous. That is, em is, this we have done in our first part of the theorem, the first part of the proof. Em is the set of points of the closed interval a b at which f is not continuous. And you see, f is not continuous means we can define em like this. Em is those points x in the closed interval a b such that oscillation of f at x is greater than or equal to 1 by m. We have earlier used this result in the first part of the proof. When oscillation of a function at x is greater than a, then the function is not continuous at x, and that a we have taken as 1 by m. So, oscillation of f is greater than or equal to 1 by m, then the function f is not continuous at x, and em contains those points where the function is not continuous. So, that we have selected for em. Now, we shall consider the further as em. So, this em must be of measure 0, because what we have assumed is f is continuous at almost every point. F is continuous at almost every point. This em must be of measure 0. Now, by hypothesis, em is of measure 0. A property holds at almost every point in the interval means the property, the set of points where the property does not hold is of measure 0. So, that means em is the set of points where f is not continuous, and therefore, em must be of measure 0. So, by hypothesis means this assumption em is of measure 0. Therefore, by definition of set of measure 0, so this set can be covered by a countable number of union of intervals such that the sum of lengths of these intervals add up to less than epsilon. So, then there exists, then em can be covered, or yes, em is a subset of union of in, countable union, that may be 1 to infinity, where in are the component intervals of this closed interval a b, where so I shall write where each in is component interval of AB such that, and further next is the sum of lengths of this in, that is summation n taking value 1 to infinity of in, that is length I1 plus length I2 etc. up to infinity. so is less than some given number, and that number we can take epsilon. Here we are taking that as epsilon. Epsilon is arbitrary, so that can be selected at our choice. Here we have taken that as epsilon by 2. Here we can take it as epsilon by 4, 10, etc. And we are taking here purposefully it is a epsilon divided by twice oscillation of f on the whole interval AB. So this is a positive number, and therefore this is a small quantity, and this sum of lengths these intervals are to be selected such that sum of lengths of this interval is less than this quantity, and we shall assume this as 3 because we are using these further. Here where it is assumed that this omega or oscillation of f on the closed boundary interval AB is greater than 0, positive quantity, that we shall assume. And now you see EM is of measure 0, that means EM is countable set, and therefore EM becomes closed. Now EM is closed and therefore it is compact. Now EM is closed and hence is compact. And what is the property of compact sets? Compact sets have a finite subcover. So here what we have written, it is a cover of EM, and that EM is covered by infinite number of open intervals IN. So where each IN is a component open interval, component open interval of AB. But because EM is finite, EM is compact, this covering must have a finite subcovering. So EM is compact, and hence therefore there exists finite number of open intervals. Finite number of, I shall write here, so this I shall put in bracket, finite number of open intervals. We will denote these by IN1 up to INK. Such that now this EM is covered by this. EM is covered by union of this INK. That means this can be written as INL. L takes value 1 to K, and so EM and the sum of the lengths will be less than or this, or we can consider only this much, that is EM is covered by this IN1 and so on. Now we can consider this as AB, the closed interval AB. See the interval is A to B, and we have divided it in component intervals, and EM is covered by these, means the points of EM will be in these component intervals. Now if we consider this interval AB, so if AB is, we can consider as AB is minus these component intervals I1 etc. IN1 union up to INK. If you subtract this, then this will contain, see these are open intervals, and what will be this? This is closed interval, and this means the complement of open interval, because we are subtracting open intervals, and therefore this will be closed intervals, is the union of, this will be is the union of closed intervals. And we shall denote the intervals, these intervals as J1, J2 up to Jp. So this is that we are considering like this. Suppose this is the interval a to b, and we have some of these components are denoted by in1, ink up to ink. Suppose it has these number of components. In that, some component intervals are in1, etc., and that we can write as, see, this can be taken as suppose this is in1, and up to that can be ink, see, in2, etc., and this may be taken as in3 and so on. And remaining, so if we subtract this union of these intervals, remaining will be j1, j2, jp, etc., and therefore this is j1, j2, etc., this will be j3, and last is jp. So that means the interval a to b is divided in two types of component subintervals. One is in1, in up to ink, that cover em, that cover the points where the function is not continuous, because we have defined em is the set of points where the function is not continuous. There are some points of discontinuity, and that these points are contained in this em, and em is contained in these component intervals. And what are the remaining intervals? Remaining intervals are j1, j2 up to jp, and there these interval contains those points where the function is continuous. So that means it is divided in two parts, and thus we have here. So this we are also requiring this part, and now thus the closed interval AB is equal to union of these component intervals in1 up to ink and j1 up to jp. So this is in1 union up to ink union these in1 up to ink and union of j1, j2 up to jp, j1 union up to jp. So this is that we have considered the division component intervals of the open closed interval a to b. Now further we shall consider these intervals ji. Now or further I shall write here. Now x belongs to ji. Now we have oscillation of f at x is greater than 1 by m, or that is less than 1 by m, that is less than 1 by m for x belongs to ji, I taking value 1 to p. So what is the meaning of this? If x is in this interval j1, j2, jp, then the function is continuous at x, and if the function is continuous at x, the oscillation is less than 1 by m, because we have considered em is the set that where the function is not continuous, oscillation is greater than or equal to 1 by m, and therefore there are two types of oscillations we are considering. The function is continuous at x, the oscillation is less than 1 by m, and the function is not continuous, the oscillation is greater than or equal to 1 by m. So for this interval x belongs to ji, the oscillation is less than 1 by m. Now we consider if tau I is the component intervals of ji, if tau I is the subdivision of ji, we have by the lemma. See, here we will use the lemma. So what is the lemma that we have proved? Upper sum of f on tau I minus lower sum of f on tau I is less than the length of this interval into a, And what is a here? A, it is less than 1 by m, that means a is here 1 by m. See, please you refer the lemma, and then this will be length of ji, the interval is ji, length ji divided by m. So this we will have, and now we will suppose this result as 4. So thus now we will consider the upper sum minus the lower sum on the whole interval a to b. Now we will have next upper sum of f on sigma. Further we should consider sigma as the subdivision. Let sigma be the subdivision. We shall select the subdivision sigma containing these component intervals. Let sigma be the subdivision of AB containing the component intervals or consisting the component intervals. See, the component intervals we will first consider J1 etc. J1 J up to JP, and these IN1 up to INK, and these are open intervals. We should consider the component intervals as closed, and therefore we write the closure of this. Closure of this is a closed interval. IN1 is open, we consider the closure, that means it will be closed. IN1 bar and so on up to INL, last is K, INK bar. So sigma has these component intervals. Now we shall form the upper sum, difference of upper sum and lower sum. So that will be so I shall consider it here. Now upper sum of f on sigma minus lower sum of f on sigma will be equal to, or that is the oscillation in this. So this is to be considered first upper sum of f on these intervals tau I, and tau intervals are the intervals taking the components will be J1 to JP. So tau I are the subdivision of Ji, and therefore this will be summation I takes value 1 to p, upper sum of f on tau I minus lower sum of f on tau I, that is first part, plus now after considering this, what we should consider is the component intervals IN1 to INK, and that I shall write. So we should remember this so that I can write here. So this is length of IN we are going to use, and is less than epsilon divided by 2 omega f oscillation of f on the closed interval AB, that we should remember, and then I shall write here, that is plus summation here we should consider as k, see this we will write L takes value 1 to k, and maximum value of f on this interval INL minus minimum value of f on the interval INL into the length of the interval INL. See, this is into the length of the interval INL. That is, upper sum is the difference of maximum value minus minimum value of function on that interval, and therefore we have divided it in two parts. See, this J1 to JP, that is written directly in terms of upper sum and minus of lower sum, and for the remaining these component intervals we are express this in terms of maximum value of the function minus minimum value of the function into the length of the interval. And now you see what is this upper sum minus lower sum of f on tau, it is here, that is less than length of ji divided by m. So therefore that will be less than, that is less than summation, and this m is fixed, so we can write it outside the summation, 1 by m summation of ji, length ji, and I takes value 1 to p. So length of ji, and what is the remaining part here, maximum value of f on this minus minimum value, that is oscillation, maximum value minus minimum value is oscillation. So that I shall write plus summation L takes value 1 to k, oscillation of f on this INL interval into length of the interval INL. So this we have written, this is oscillation, and this is written by 4. So this is by 4. Again this will be less than, you see this is further less than, what is the length of ji, all these, length of ji will be certainly less than length of b minus a, or that means length of this interval a to b. The length of interval a to b is b minus a, and we have written earlier this b minus a divided by m is less than epsilon by 2. So this will be less than b minus a, and thus the expression will be less than b minus a divided by m, and that is less than epsilon by 2. So the first term will be less than epsilon by 2. That means this expression is less than epsilon by 2 because this quantity is less than b minus a, and plus, so plus what is this? This is the oscillation from L taking value 1 to k, and therefore this oscillation will be less than, certainly less than oscillation of f over the whole interval, that is the interval can be taken as from first component to last component, and therefore that is less than oscillation of f on the whole interval a to b. This oscillation is less than the oscillation, these are the oscillation of the function in these component intervals, and if you consider the oscillation of the function in the whole of the interval a to b, this will be certainly less than this oscillation, and this is independent of the sigma. So we should write it outside. And what is the summation k taking value 1 to k of this INL length, and that can be written as less than summation k takes value, or you can consider here k takes value 1 to n length in. So length ik, the whole length, or that can be taken, earlier we have taken it in terms of infinite numbers, that I shall write this is n taking value 1 to infinity in. And that means if you make the infinite intervals, then this length will be less than this number of infinite intervals. Why we have written like this? So we are replaced these quantities by bigger quantity. So this is less than epsilon by 2, this is less than omega of oscillation of f on the whole interval AB, and this is less than this entire length from A to B, component intervals length, sum of lengths. And we have by the third relation here, that is this is less than, or that will be less than, this is less than epsilon by 2 plus oscillation of f on the closed interval A to B into, and we have, see you refer third, what we have written third is summation n takes value 1 to infinity of length in is less than epsilon divided by twice omega oscillation of f on the interval A to B. So this was our third result I have written here. This is the third result. Now we use this result here, and therefore this will be less than epsilon divided by twice omega or oscillation of f on the interval, whole interval A to B. Now what does this imply? So this is epsilon by 2, this term cancels, and this is epsilon by 2 plus epsilon by 2. So therefore this is equal to epsilon by 2 plus epsilon by 2, and that is equal to epsilon. This expression is equal to epsilon, and thus finally what we have, upper sum of f on sigma minus lower sum of f on sigma is less than epsilon. Thus we have upper sum of f on sigma minus lower sum of f on sigma is less than epsilon, and this is what we wanted to prove. This shows that the function is Riemann integrable over the interval a to b by theorem 1. So this is what we wanted to prove. And therefore f is Riemann integrable. F is Riemann integrable over the closed bounded interval a to b, and this completes the entire proof of existence theorem. So we have proved the theorem in two parts. In earlier lecture we have proved the first part, that means assuming f is Riemann integrable, we have proved f is continuous at almost every point in the interval a to b, and now in this lecture we have proved the converse part. We have assumed f is continuous at almost every point in this interval, and we have proved f is Riemann integrable, and to prove f is Riemann integrable we have proved this result. So please go through the proof and try to understand. Thank you for watching the lecture.